Hey everyone, this is Mrs. Harding again. Today we're going to go over activity 2.1b. If you remember, section 2.1 was on describing a position in a distribution. In 2.1a, we finished with doing standardized scores within a distribution using the mean and the standard deviation. And if you take a look at what we're going to cover today, there's really only one lesson objective. We're going to describe the effects of adding, subtracting, multiplying, and dividing a constant to an entire distribution and what effect that has on the summary statistics, which is essentially what we were doing when we were standardizing scores. We were taking any data value and we were subtracting the mean, dividing by the standard deviation. So we're going to take a look at these linear transformations of a given data set. So if you go to your activity, you can see on the right side, there is a list of the average temperatures for July in 25 different cities. If you would like to enter these in your calculator, please pause and enter them in. We will be doing a little bit of work in the calculator with these, so it might be helpful for you to work along. Okay, what you can see on the side is the summary statistics, which is the same thing that you would have gotten if you had entered it in your calculator and done a one variable stats. Let's take a look at what the shape of the distribution is. If you go to the next page, you will see a dot plot of all 25 values. And if you were going to describe that distribution, you would say it's symmetric. You have a median of 87.2, an IQR of 6.8 with outliers at 71.6 and 105.9. Now you might be a little confused just briefly there because I said it was symmetric, but then I used the median and IQR to describe it. This is a great example of a relatively symmetric distribution that has outliers. So because there are outliers there, you do want to default to the median and the IQR as your measures of center and spread. All right, well, let's take a look at this next question. It says, suppose now that the global temperature increases by 3 degrees. Discuss what you think happens to the dot plot of the new data and recalculate the 5-number summary, the IQR, mean, and standard deviation. Imagine for a second what will happen to all of these values as it increases by 3. What will happen to the shape? What will happen to all of those summary statistics? We can do this fairly quickly in the calculator. So if you have your data values entered into your calculator, you have something like this. We certainly do not need to take the time to go through and add 3 to all of these things. Here's what you're going to do. You're going to go over to the label L2 and you're going to write a rule for the entire list. The rule for the entire list is that it is L1, which you get from second 1, plus 3. And it will populate the list with list 1 plus 3. And so then you can take a look at one variable stats now for list 2. So remember where that is, stat, over to calc, one variable stats is here. We're going to find one variable stats now for list 2 and take a look at the information there as compared to what you see on the first page. So you notice the mean is 3 degrees higher. The standard deviation is exactly the same. The minimum is 3 higher. The Q1 is 3 higher. The median is 3 degrees higher. Same thing with Q3 and the max. But the IQR, which is the difference between Q3 and Q1, actually remains the same. Hopefully that should make sense to you. If everything is just shifted up 3, the distance between points hasn't changed. So we talk about the measures of position, which are the minimum, the median, the maximum, Q1, Q3, the mean. All of those things don't change. Excuse the screen flipping there. All of those increase by 3. The measures of variability, however, that's IQR, range, standard deviation, they actually do not change. The distance between points has not been altered at all. Everything has been just shifted up 3. The shape of the graph also does not change. So let's think about what would happen if instead the temperatures increase by 5%. Do you think the measures of position will change? Do you think the measures of variability will change? Do you think the shape will change? Well, we can go back to your calculator again. I'm going to go to my lists. You can clear out list 2 if you don't want it there, or we can just build on this. And we can say, well, the rule for L3 is going to be L1 times 1.05, which is an increase of 5%. You'll see the new temperatures filled in there. So then if we run a one variable stats on list 3 this time, we can take a look at how everything has changed. And you'll notice this time that not only has the mean changed, but the standard deviation has also changed. And because Q1 and Q3 changed by different amounts, the IQR has also changed. So what this should tell you is that multiplying or dividing by a constant, apologies, my screen is not going to scroll again. There we go. Changes everything except for the shape. So all measures get multiplied by 1.05. They all increase by 5%. The measures of position change by 5%. The measures of variability change by 5%. But the shape does not change. And this is just what parts D and E on here are summarizing. So again, adding or subtracting the same value to each piece in a set of data will change measures of position by exactly the same amount, but will not change measures of variability or shape. When multiplying or dividing every data value in a distribution by a constant, it will change measures of position and measures of variability by that same amount, but the shape does not change. Okay, so then let's take a look here at what we were discussing earlier. These linear transformations and how they can affect measures of position and measures of spread. So in here, it says in 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. At the end of one particular month, a businessman gathers information from the odometers of the cabs and obtains the following information. To verify his books, he wanted to know what the average and standard deviation was for fares that month in dollars. So here's all we need to do. He's got the mean and the standard deviation of distance. We're going to figure out then the mean and standard deviation of the amount of fares that he's collected by doing a linear transformation. So what is going to change? Well, the mean fare is going to change because you've multiplied by 2 and added $2.50. It's affected by the multiplication and by the addition. So $15.50 should be his average fares collected that month. The standard deviation, however, is only impacted by the multiplication by 2, by the $2 per fare. Adding the initial $2.50 does not change measures of variability. So to figure out what the standard deviation is of the fares that were collected, you would just put 2 times 2 to get $4. The shape will not change. Okay, let's connect this back to z-scores. Remember the test data that we were looking at for one of the classes. These were the tests on a statistics in a statistics class. And then the summary statistics were given at the bottom. Mean and median were both 80. Standard deviation was 6.07. So what would happen if we standardized every single score in that list? Before we had just done Jenny's score of 86, but what if we went through this whole data set, standardized every score? What kind of mean and standard deviation would you be looking at? Well, remember how you come up with a standardized score. You're going to take an X value, you're going to subtract the mean, and you're going to divide by the standard deviation. So we're just doing a linear transformation on each. So how will the mean be affected? Mean minus itself will be 0. So you'll have a mean of 0 in the new distribution. How will the standard deviation be affected? Well, standard deviation won't be impacted by this subtraction of the mean. So essentially, you'll have standard deviation divided by standard deviation, which gives you a standard deviation of 1, and the shape will remain exactly the same. So when you standardize all the scores, you end up with a new distribution that has a mean of 0, standard deviation of 1, and retains the same shape. And that is all for this lesson. As always, if you have questions, please let me or Mr. Bowman know.